Good? Okay, perfect. Thank you so much everyone for showing up. Today I'm going to be talking about the recent work with Shi, Digitized Counterdiabatic quantum algorithm for protein folding. So, yeah, this is the outline. First I'm going to recap about what I've been doing as a part of my PhD. And then I'm going to be talking about protein folding in general, the algorithm, performance analysis, experiments, and last we'll discuss the challenges and the overall conclusions of the work. Okay, just a recap of what I've been doing. I have given this talk previously, but just to make sure that everyone is in the same page. My job as a PhD is to combine hybrid quantum classical optimization algorithms with shortcuts to adiabaticity. So yeah, when I talk of shortcuts, I talk about counterdiabatic driving. So you have adiabatic Hamiltonian, which I think all of you might know already. And you start with a simple Hamiltonian HM in the ground state, and you take that HM to a problem Hamiltonian HC with a scheduling function lambda. And then if the scheduling function is slow enough, you prepare HC in its ground state with high success probability. But you usually don't want very slow lambdas, so what you do is you add a counterdiabatic term which will suppress the non-adiabatic transitions for finite time. So you speed up the process by adding some gauge potentials, and these potentials actually suppress the non-diabatic transitions. So how we do that? For finding a perfect CD term, you need exact spectral properties, which we don't have all the time. So there is a way to find an approximate CD terms. So it's proposed in this paper, and this is the form. So you do nested commutation operations, and then you find approximate CD terms. And this approximate CD terms you add into your Hamiltonian, and then you can get a faster convergence to the solution. So this is the main idea of counterdiabatic driving. So when you talk about hybrid quantum classical algorithms, which looks like adiabatic quantum computation, you talk about QAOA. So QAOA, you have these two unitary operations that you do iteratively, and then you have two parameters that you optimize by classical optimization. So your goal is to have this two mixer and Hamiltonian terms, and you at each iteration you optimize alpha and beta so that your cost function, whatever it is, in our case it's the expectation value of the Hamiltonian, is minimized. So this is the full unitary thing. You have repeated operations, and then you optimize at each iteration, optimize gamma and beta so that you can reach to the ground state. So this is, yeah, you know already. Okay, and this was my previous work, in which the idea was, so QAOA looks like adiabatic evolution, right? Because you have this UP which looks like the tautorization, and so maybe it's interesting to add a CD term, because CD has shown speed up in literally every adiabatic thing that I know. So maybe it's also interesting to add in hybrid optimization algorithms and check if it works or not. And yeah, it kind of worked. So what we do is we add one more term with the Hamiltonian and mixer term, which we call CD term. And how this CD terms we find it approximately, because it's approximate algorithm. So we nested commutators with finite number of order. So it's like first order nested commutator, so it's just 1. If you go for 2, it's 3, so something like that. And you do this operation, you find terms, and then you put it. And one more advantage is that you get one more free parameter. So this parameter is you have multiple ways to find this parameter, but in our case, as we are dealing with classical optimizations, we keep that as a free parameter. So instead of getting just 2 parameters per lay, you get 3 parameters. So your degrees of freedom increase, and then you have counterdiabatic driving in some sense, so that you can get to the solutions faster. Yes.
So which of these parameters would tell you the value of lambda, the strength of the drive?
Exactly. So this is. Yeah. So the notion is not completely. So that's what I'm trying to tell you. That is not exactly adiabatic evolution. So you don't have the notion of lambdas per se. But if you want to get connected with the adiabatic evolution, so you have e raised to minus I h dt, right? So the dt is a term. So what you are doing is you're trying to change the DTs, so you're trying to change the evolution times, and this evolution times are by classical optimization, so that you can get to the solution. This is what I can give you an intuitive picture.
Looped, right?
Yes, exactly, it's looped, yeah. Yes.
So far, you have managed to do something like another layer. Right?
Exactly.
The UA approach.
Exactly.
Okay, maybe it's quite naive, but why only a single, an additional layer? Why not 2, 3, or 4, depending on additional parameters? It's because this is already closed.
Yes, exactly. So you can do it. You can do it for sure. So if you take for example this, if you take this nested commutator, you get 5 terms, for example. Okay, and you get a set of terms, and then you can put all of it. It's fine with one additional parameter each time. But what our goal was to build a more structured algorithm. No, so instead of 2, just increase 1, so 2 instead of 3, and there's just one gate with one parameter. So that's kind of thing. But yeah, you can take any of the gates that you want, and it still works. So depending upon the circuit depth and stuff, you have to, if you want to think in terms of experimental, then you have to be a little bit smart, because yeah, but yeah, true, it's true, you can put any number of additional gates and it should work. Yeah. Yep. Okay, so this is the conclusion from this, is which I shown in the last seminar, that it works. So you can just accept it, because yeah. So okay, so now we go to the protein folding thingy. So protein folding is an important problem in biology. I don't know much about it, but yeah, for me it's very important problem. And for here, in our case, we tackle protein folding as an optimization problem, right? So it's, for me, there are 2 kinds how protein folding is solved. One is machine learning, where you have lots of proteins and then you learn from them, and someone gives you a new protein, you just apply. Another one is this, so you have it as an optimization problem. How do I solve it? I tackle it as a, okay, how do you say lattice or lattice? I say lattice, so lattice is this word, okay? Yeah, so you solve it as a lattice problem, and where amino acids are just beads, okay? So I don't care what's inside, I just care A, R, N, D, I just care about that, okay? And for each amino acid, I know the interaction with the other one. So I know the interaction energy between A and R, R and N, A and N, everything. So I have a matrix of all the amino acids and all the interaction energies in between them, I know. So what I do is I take a lattice and then I put my beads in the lattice such that the whole conformation energy is minimized, right? So I take one, put another, and the folded will be the most stable configuration, so it will be in the most minimum energy. And my job is to put it so that the energy is minimized. So that's the optimization problem, okay? Yeah, so 3 important things that we have to decide before approaching the problem. First is type of lattice, so you can do 2D, you can do 3D, you can do tetrahedral. So 2D we have 4 directions to go, 3D we have 6 directions to go, and in the middle there is a tetrahedral lattice where you have 3D structure, but still you have 4 directions to go, okay? We have to also select type of encoding, how you encode the information. So we have 2 ways to do it. First of all, it's position encoding, where you encode the position of your bead, your amino acid, right? So 1 qubit will show the coordinates of the amino acid, and then it's like this. So for example, if you have this, then 0001 will show this one, 0010 will show this one, and then this is the interaction. And second one is a turn encoding. So in turn encoding, we, instead of encoding, yeah.
So when you are writing the Hamiltonian, you said that you know the energy between
Yes.
the different amino acids.
Yes.
But this energy depends on the distance. If you are studying not the quantum state and the energy, but also the conformation of the
Yes.
spatial
Yes. Yes.
so your Hamiltonian also depends on the position.
Yes. My Hamiltonian depends on the position, and my Hamiltonian, I will also have kind of, I will define a distance, like for me it's 1, for example, and then if two amino acids are at 1 distance, it will be a connection. That's the thing. I will explain in the next slide, it's there. Yeah, perfect. So, so first one is the position encoding, second one is the turn encoding. You just encode the turns each amino acid takes, and you can select any one of it, and then there are types of interactions. So there are 2 types of interactions, where one is hydrophobic polar, so it's just -1 and 1 depending upon if 2 amino acids attract or repel, and the other one is this, I don't know how to say it, I call it MJ interactions, which are arbitrary, and this is the paper where these guys study the residue interaction energies, and they give just a matrix of every one of the interactions. Right? For me, it's just a bit. So like A with R, I know the interaction. It's just a number. So that's it. Okay. Yeah. So for our work, we select tetrahedral, turn encoding, and MJ interactions. Right. So this this one, these three are my choices. I mean, you can play with it, but yeah. Yes. Yes. Sorry.
3D.
Tetrahedral is 3D. Yes. So you have going and yeah. It's good because it's 3D and still I have to encode only 4 directions, right? Instead of 6. So it's resource efficient. Okay, so this is the problem. So this is a lattice, and then I have given 1, 0, 1, 2, 3, and 0, 1, 2, 3 will be encoded by 0, 0, 0, 1, 1, 0, and 1, 1. And I have 2 inverted 1, 1 P and 1 Q, and I create a mesh out of it. And then this, for example, you say it's 0, 2, blah, 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 and then you have a series of turns so that the energy is minimized. Okay, this is the problem. Okay, so I have in my logical qubits, I have 2 types of qubits. The first qubit are the confirmation qubits, which are pairs of 2 qubits, which will show me the turn. So like 0, 0 is 1 turn, 0, 1 is 1 turn, and then you have lots of, depending upon your amino acid chain, you have this string of qubits which will show you the turn. And second type of qubits are 2 indices qubits, which are the energy. So for example, if I want to know if there is a connection between first amino acid and fifth amino acid, so there Qij, if there is a connection, so Q15, if there is a connection, then Q15 will be 1, and E15 is the energy that I get from the matrix of MJ interactions. So if there is a connection between first and fifth, then this energy will be applied to the Hamiltonian. So this is interaction, so it has both. So confirmation and interaction. The total qubits are QC and Q interaction. Yes.
Sorry.
Yes.
So the QC, they encode what did you do in that turn?
Exactly. Which turn did you take? So I have, for example, I have 3 amino acids. Okay, A, B, and C. So you have A to B, you have 4 turns you can take. Right? When you go to B to C, again you have 4 turns you can take. So at every turn you will, so for example 0, 0, 0, 1, so it's 0, 0 is 1 turn, 0, 1 is 1 turn, so like you will get the direction of the turns. And then after everything is over, then you will have some connection, which I can show it later. And then you have a connection, and then yes.
I was confused because it looked like some kind of enumeration, but it could be just like 1, 1, 0, 1, right?
For sure.
I was confused, like 0, 0, 0, 1.
No. Yeah, this is because of the spatial symmetry. So 0, 0 and 0, 1, because these are first 2 turns. So like the first 2 turns, it doesn't really matter in space what they are, right? It's like we have a symmetry. So that these 2 are fixed, and then you can have anything.
Okay.
Yeah. Right? So you can have any possible turns. Okay. So yeah. So this is the Hamiltonian. I'm not going to get into full detail of it because this is already been done. So yeah, I will concentrate on the algorithms part, but it has 3 terms. So first 2 terms are the constraint, and the third term is the interaction Hamiltonian. So first shows the growth constraint. So you have to penalize overlapping, right? So you cannot take turn number 1 and then again go back. The amino acid will overlap. So then you don't want that. So when this happens, this Hamiltonian will increase the energy of the system. So it is a penalty. Second one is the chirality constraint. So for example, if you have an option of adding side chains to the protein amino acid sequence, and then you have to follow, it's not actually chemistry chirality, but you have a certain constraint that you have to follow. For example, you make a rule that if there is a side chain, it will be in the second direction. So then you have to follow a certain rule. And that's it. It's not actually chirality of chemistry, but yeah, they have certain rules that you can follow. And the third one is the interaction Hamiltonian, which I already told you. It shows the total interaction energy depending upon the contact. Okay, so you convert everything into your Ising Hamiltonian, and the Hamiltonian looks like this. This is a 5 local classical Ising Hamiltonian, and all the interaction terms are arbitrary, and it depends upon which protein you select and the interaction between them and all the constraints that it has. Sorry?
The indexes. IJKL.
Yeah, it depends upon the problem.
But they are lattice sites, or what is the...
Yes, they are lattice sites. Yeah, they are lattice sites. So for example, if you have 2, 3, then J2, 3 will be the site of the graph of the lattice.
This site is not populated, or you have a 0 in the coefficient?
Yes, yes. You have the 0 in the coefficient, so it's missing. Yeah, that's it.
So I mean, if I have something occupied the position 1, but not the 3, and I have J1, 3,
Yes.
then this is
0. Yes, yes, exactly. It's 0. So yes, so our problem is, so now I don't care about protein folding anymore. So I have a Hamiltonian and I need to find the ground state of the Hamiltonian. This is our problem now. So I need to find a ground state of this Hamiltonian, right? And Gijs and His can be arbitrary. So yeah, and this ground state of the Hamiltonian will contain all the information of the protein that is required, and then I can draw proteins. So that's it. Okay, so now how we do it? I will go back to counterdiabatic driving. Yes. Sure.
Okay, maybe I don't know, but this, all of them are sets, right? Sigma set, sigma
Yes,
set.
it's classical, yeah.
Okay, so, my naive question is, okay, this looks pretty classical, pretty diagonal, doesn't
Exactly.
generate too much entanglement. I would say nothing, almost. Right?
Yeah, almost nothing.
Classically efficient to calculate.
I don't know, yeah, this is a question that everyone asking me, but I really don't know. But the thing is that I know works that show that even if there is no requirement of entanglement does help to reach the solution faster. Okay, so if you have classical problems, I will show you the paper. It's adaptive QAOA paper related to that, and they show that if you have in your circuit answers you have entanglement, and even if the problem is classical, there might be an improvement. So that's my answer to that. But yeah, if it's like a classical Hamiltonian, so maybe it's
Because
after a point of time.
what I would do, again, naively, because I don't know too much about this problem, is to actually all of the terms commutes.
Yes, exactly.
So you have to be as exponentiate each individual term. Looks pretty analytical.
Yeah. Exactly. It's easy to solve classically, but optimization, if you want to do optimization, only this part if yeah, sorry, okay, only this part if Jij and Hi are arbitrary is NP hard to solve.
Okay.
So then it's like you have to, yeah, but classical analysis I don't really, I will be very honest, I don't really know how complex is this classically, but yeah, that's what I can offer. Yeah.
Yeah, probably depends also on the value of the constants. For an
Exactly.
arbitrary value of the constants,
Exactly, it's-
hard to classify, right?
Exactly, that's it. So I know,
Hard, yeah, in the sense that you have an exponent in the size of the lattice, it's exponential, the search space.
yeah,
The classification.
yeah, exactly. Yeah, so one result that I
That's
know.
also the same with quantum, right?
Yeah. I agree with that point.
Okay, sorry.
Yeah, it's fine. Yeah, for sure.
Sorry, but I still don't understand the Hamiltonian, because as I asked before, is how, so for instance, you have different kinds of amino acids. Where is the sum? Because you have position I, J.
Yes. No, but this IJ doesn't show actual positions, right? So if my position is 1, 5 in the lattice, do you mean like that? No, it's not, because I'm not encoding positions anymore. No, I'm encoding turns, right? So.
That is what I asked you before. IJKL.
Oh, maybe I misunderstood then the.
So I have to restart again.
Okay, you
So
can.
IJKL is an index over what?
What do you mean by index over what?
What are you-
So for example, I'll explain what. So you have to go to this paper. So if you are doing, if you want to find HGC, for example, you have to multiply multiple terms. So you have 1 minus xij, because if you overlap, you'll get a penalty, and then you have to do this crazy logical thing, and then you put of each x, you put 1 minus sigma j by 2, right, to convert it into a quantum, not a quantum, but like convert it into Ising spin, and then you product it all, and then you will get a 4 sigma j term. It's hard to explain because it's mathematical, but yeah, you get.
Don't understand what the sum, the index is IJKLM.
Yes.
From what to what? Are the units?
Yeah, it's problem dependent. So for each problem, for example, I'll tell you one thing. I try to explain in a better way, I guess. Okay. If I have in one problem, I have a connection between first and fifth. Okay. First and fifth amino acid, and then first and fifth amino acid. Right. First and fifth amino acid, And then to encode this connection, I have to do some logical things in my Hamiltonian. Okay, so to do that logical things, maybe I have to take a product of 5 terms, right? These terms are 0 1s, for example, right? And then you put this connection into the Hamiltonian, and then you product it, and then you get a term like this. So it's problem dependent. That's what I would say. It's really hard to explain it because it's logical, but it's math. So I mean, yeah. But so for example, if you want, so if you tell me, oh ij, let's just consider this term. So you have n into n minus 1 by 2 maximum terms in a. So if you have 2 body terms, then you have or
You have this Hamiltonian for every 2 amino acids.
no, it's like a full.
Okay, then but it doesn't matter. Okay,
Yes.
When you have, for example, in the last term several sigma sets,
Yes.
so are they from the same subspace or they represent different subspaces?
The same subspace. That's what I would like to say.
It's just a 2 by 2 matrix.
Oh, no. Okay. I got the point. This ij will be from 0 to number of amino acids. So number of amino acids in your protein.
I didn't hear.
Number of amino acids in your protein.
Okay, perfect.
Right? Now it's making sense?
Could be. At least I have an answer. Okay.
Yeah.
Okay.
I have a question.
Yes.
Because I was-
But what I can do is I can share this paper so that it's easier for you guys, but it's fucking difficult to
Yeah. But then.
say maths. So that's it.
Okay. Are you going to ask something, Ruben, or?
Yeah, I want to ask something.
Yeah, sure.
I hope it's quick, but if it's not, then just...
For sure.
What I understood was like the indices were in the qubits.
Yes.
You somehow map the problem of the physical interaction
Exactly.
to the state of the qubits.
Yes. That's what yes.
And that's the Hamiltonian. So the Hamiltonian has nothing to do with the energy of the protein, but it's like a mapping of that energy
Yeah.
of the protein to the qubit system.
Exactly. Yeah, that's it.
So the indices are not over the amino acid, but over the qubits that you are using to represent those amino acids.
Yeah. That's
so
true.
The Ij doesn't represent a coupling between 2 amino acids, but
No. Exactly. Exactly. That's it. GIJ doesn't represent the interaction between 2 amino acids. It represents interaction between 2 qubits, which I will map.
Okay.
Right?
You have a thing from the interaction between amino acids, but maybe it's not exactly the interaction between.
Exactly. Yeah.
Maybe not. It's not, right?
Yeah. That's what I said. No. It's not. So GIJ is not the interaction between 1 and 2. It's just the interaction between my Hamiltonian, right?
Yeah.
Okay. Harder than expected to explain. Yeah.
Now I have a question.
Sure.
How do you model these age?
Yeah, it's the same question that everyone is asking basically, but yeah, I'll share you the references. It's like a 20-page appendix to the reference, and it's hard to explain all the 20 pages. So
Because like in quantum chemistry, this is basically like a really difficult, impossible problem to solve. Like finding.
no, but quantum chemistry is not classical. No, quantum chemistry, as far as I know, it's not. It's you have X and Z gates. No, you are working. Yeah. So for me.
My knowledge is that you start from some purely classical stuff and then you start to step by step add some little quantum features, right?
Yes, exactly.
Minimize.
Yeah.
This is like a set of constants, right?
Yes, exactly. This is a set of
Okay,
concepts.
but it's a knowledge which is by itself complicated.
Yeah. Yeah. It's not that complicated, but yeah, I mean,
It's like a lot of accumulated knowledge.
accumulated knowledge. Yeah, that's it. So basically, okay. Protein folding aside, if you don't want to get into it, you have to find a ground state of this Hamiltonian, okay, which I will try to do now. Yeah, because okay, it's hard to explain, but anyway, it's fine. Yeah. Okay, so now we get into a point when I know some things. Okay, so we have our CD Hamiltonian, and this you already know. So this is a mixture. This is the cost, and then you add one term, which is called the CD term. Okay, now at lambda dot tends to 0, this term will vanish, and you will get your adiabatic evolution, right? But I want you to imagine a situation where for all times t, this condition is satisfied. So for all times t, lambda dot of t is always more than lambda of t. Okay. So now for that, if this situation is satisfied, this term dominates, right? Because at every time you have a larger coefficient for the Hamiltonian, and this term is negligible, the full term, right? Yeah. So what you can do, because you have to find approximate solution, what you can do is you can just completely neglect the term and you can just implement these terms, right? So this is my motivation for the answer. Do you know? Okay, you guys look so confused right now. Can I repeat?
Yes.
Okay. So this is the counterdiabatic Hamiltonian. With me?
Yeah.
Right? So this is the CD term. I find some arbitrary lambda, arbitrary scheduling function, okay, for which this condition is satisfied. Yeah, sorry. Okay. So if I find some arbitrary lambda for which this condition is satisfied, this term will dominate, because at all times t, lambda t will be very high with respect to lambda, and this term will dominate to the whole Hamiltonian, right? And so what you can do is you can completely neglect this term, and then you have only this term which will be your Hamiltonian. Okay, you can stay with me for a while because I will explain why we do it. Okay, so in QAOA, what we do is we take the whole Hamiltonian and exponentiate it, right? So in QAOA, you have full Hamiltonian, not this term, these two terms, but it will be very costly because when you want to go to an experiment, you have to implement this term, which is a 5 local term, which is very hard to implement. So now the idea is this. So when you do QAOA, you implement full evolution of the Hamiltonian. Right, so you have 5 local terms because there is a 5 local term in the Hamiltonian. So instead of implementing full evolution, what you do is you find counterdiabatic terms, and instead of implementing counterdiabatic terms over the QAOA, you just remove the QAOA part and then just implement only CD terms. Right, so this is the inspiration behind only CD. Pablo in his master's thesis gave I don't know how to say, proof, or he did something with only CD. So this is the physical explanation behind why only CD answers can be possible. So to conclude, what I do is I have a Hamiltonian, I find nested commutators using this formula, okay, and then I implement just this, so just the CD terms, okay, nothing else. So it's just CD terms implemented, and then you have free parameters, okay. So this is the idea. Yeah. So instead of, you have seen previously that with QAOA I implement one more CD term, right? But now I just remove the QAOA part. I just implement CD terms, and then you will ask that, oh, how can you find this lambda, that this condition is always satisfied and stuff? So my answer to that is I don't. So what I do is I put this lambda as an optimizable parameter, so that my classical optimizer will try to find a good solution to the problem. So I have a hybrid algorithm. Okay, I have only CD terms, and instead of this lambda, I have optimizable parameters which will take me to the ground state. So that's the idea. That's the idea because, and why this is important, because it will reduce the circuit depth from a huge daemon to just whatever I want, right? So, and this lambda is from nested commutators. So, okay. So yeah, so instead of adding a term on top of QAOA, we just remove the QAOA part, and then we implement only CD terms. So this is the name of the answers. It's CD inspired because it's not exactly counterdiabatic driving, but it's just only CD terms. And how do we find only CD terms? We do nested commutation with order 2, and I get full expansion of nested commutation terms. So like, for example, I take my mixture term as X, it's a simple Hamiltonian. My Hamiltonian has ZZ terms, so ZZ with X commutation will give ZY and all the funny terms here. Okay? So now, we already have an approximate thing, and this is the A, so you can choose terms from this expansion, and then you have thetas, which are optimizable parameters, which you optimize using classical optimization. So this is my full circuit. So instead of full QAO, I have just CD terms, and then I have optimizable parameters, which will be optimized classically, and this will run as a loop until I get my minimum energy. So that's the algorithm. Okay? Yes. So for this problem, I have selected these two terms. So now with five local classical Hamiltonian, you have CD terms that are 5 local. But you want to do experiment. So now I further truncate my CD term to just 2 body interactions. So I select only 2 body interactions out of the full. So there is one more truncation here, right? So my answers will have just y and yz interactions, which I will show in the next slide. Yeah, so this is the full picture. This is the answers proposed in this work. We have y interactions, and then we have yz interactions, 2 body interactions. All of the gates, all of the interactions have their own free parameter. So every free parameter will be optimized, and then you hope to get to the ground state of the solution. So at each step, you find the expectation value of the energy, and then you run it again and again, like QAOA, and then you try to find the ground state. Okay. So these are the 2 types of problems which I compare our answers with. This is the full QAOA. So in this block will have 5 local terms because full, yeah.
Have you tried to repeat the optimization with 2 body terms that does not appear in the CD term, just to check the
Yes.
terms that appear in the CD term other way terms?
Yes, I have. And it's better. It works better. With CD term, it works better. So yeah, it works better. Yeah, that's it.
Why do you say that A is hardware efficient?
Yes, I will tell you. Yeah. So I have two types of answers that I compare with. This is pure QAOA, where you have 5 local terms here, okay, which is very hard to implement in experiment. And then you have mixer. So it's just QAOA, mixer, and Hamiltonian terms. And this is the hardware efficient, where there is no information of the problem, okay, because you don't do Trotter evolution, so the answers is no information of the problem, right? It's just C naughts of nearest neighbor, and then there are just blocks of wide rotations. So from going from left to right, the hardware implementation becomes more and more difficult because this. Yeah, what was the question? Why it's hardware efficient?
Why do you say that this is hardware?
Because you have in your device, you almost have not every time, but you have nearest neighbor interactions, no?
Yeah.
But here, for example, here you can have an interaction between 1 and 3, or C naught between 1 and 3,
Yes.
right? But 1 and 3 will not be, for example, connected in IBM's device, right?
Sure. You can also have another. So this does at least n time steps. The first one. Right?
Yes. So you can do again and again, but
No. N time steps means that you have to do it. You cannot parallelize this gate.
No.
So you have n times.
Yes.
Like n gates.
Yes.
But you can also do control nodes with 1 and 2, 3 and 4, 5 and 6, and so on. And then so between odd numbers and
Exactly. Yes. That would further decrease the circuit depth. That would be
you
yes.
can reach the same level of entanglement.
Yes.
And logarithmic number of steps instead of n.
Yes, that's true. Yeah, I agree with that. But in literature, they use this kind of answers, and in the previous work also they have used the same answers. So that's why I didn't do it. But yeah, I completely agree that if you parallelize and then you do this kind of thing, you will further reduce the circuit depth. So that would be called hardware efficient in some sense. But yeah, so that's it. Okay.
I don't quite understand. So, for example,
Mhm.
in your answers,
Mm-hmm.
so the first part is you initialize every qubit in the plus state,
Mm-hmm.
and then the first thing is a single qubit gate, right? Which is on the y-axis.
Mm-hmm.
So you can either tilt each qubit to the 1 or to the 0, right?
Mhm.
And then I don't understand why do you need the rest of the multi-qubit gates? Because
You can get the solution with
the answer
only
is
y.
going to be the computational basis.
Yeah, I know.
Only need the first
Yes,
row.
exactly. That's true. And this answers we can. So the point is that I can do with only y interaction. I can get to the solution, right? But this answers has barren plateaus. So when you scale it, barren plateaus. Do you know how to barren plateaus? Sorry, I'm Indian accent. You have to. I'm learning how to develop an accent, but it's not working. Yeah. So it has been known that this has barren plateaus, so it's very hard to get to the solution. You have just y, and you try to classically optimize it. With increasing system size, it's very hard to get to the solution easily. Right? It's something called as trainability of the answers. So trainability is defined as how easy and circuit answers will be to train. Right? And just y interactions contains the solution, of course, but yeah, it would be with system size, it would be very hard to train it. to get to the ground state. That is already known. Yes.
So it's not fundamentally equal.
Yes.
B and A, just because in the B you have the only difference perhaps that you have something like a multi-qubit gate, if I'm not mistaken, right?
Sorry. In B, yeah.
You have something like a multi-qubit gate.
Yes, 2 qubit gate. So I have YZ interactions. So it's like this. YZ.
You never have so the big block there, the last one. Right?
Yes. Yeah.
Only look to validators. Yep. And which is the fundamental difference with A, right? Because in the end also A is I can imagine you can decompose everything, right? So you can write B in terms of single gates.
Yes, exactly. But this has some information of the problem also, no? Some information of the problem, because QAOA has full Trotter evolution, so you have information from the problem. It's called problem inspired answer, so it's inspired from the adiabatic evolution. It's not exactly, I just cut down some terms, so it loses the information of the problem, but still it has some information of the problem. It's like a Trotter, it's like a Trotter evolution kind of thing. But I lose some information, that's for sure. But I don't lose the full information. So it's like kind of middle of both the regimes. So I don't get full hardware efficient answers because I have. So for example, I have 1 and 5, for example, and then you need swap gates, but I don't have to use the full information of the problem as well. So it's like kind of in the middle of both of the things, and you do this to get into a regime where you can actually implement it on a hardware. Yeah. Okay. So yeah, so that's basically it. So anyone has any doubts now? Because yeah, you have. Okay, perfect. So this is the answers, and now I will do the performance analysis. I will compare the CD inspired answers with hardware efficient and problem inspired answers, both of them, and let's see how it goes. I know how it goes, but yeah. Okay, so I studied 4 proteins. This is the amino acid sequence, and this is the funny names. And the qubit, if you're interested in number of qubits, it's like 6, 9, 13, and 17. So these are the 4 proteins that I consider, and each of the letter is a amino acid, right? And you have interactions and stuff. So yeah, interactions are MG interactions. Okay, so this is the absolute performance analysis. So what I do is, when I have my circuit, I have my classical optimizer, but I need to start somewhere, right? So I have to randomize the initial points to start the algorithm. So what I do is I take 20 random instances, where in each instance I randomly start at a point. So I have some initial values of my thetas, my parameters, and then I start, and then I run the algorithm. And the graph shows for 6, 9, and 13 qubit systems the success probability. Success probability is defined as the probability of getting the ground state, right? So you can see it works okay, not that great, but yeah. So the observation is you get very high success probabilities, and as you increase with system size, the number of instances which are randomly chosen decreases, right? So for here you can almost randomly choose, and there are 50-50 chance that you might get into solution. Here it gets lower, and here it's like just 1 in 20. But this is absolute analysis, but in hybrid algorithms you are mostly interested in finding approximate solutions, not the exact solutions. So yeah, but this is exact solution that you find. So if you want that, I can do for 17, maybe it's like 1 in 40, right? So it's when the system size increases, it becomes harder and harder to find the exact solution. So that's the first part. Second part is the comparison. So I showed the circuits previously. This is 17 qubit system, which I compare with hardware efficient answers. So just Y rotations, C naughts, and then Y rotations again. So we can see that this is our algorithm. This is the hardware efficient, and the highlighted part is average of the 20 instances that I considered, right? So you can see that it converges faster than hardware efficient, which is intuitive because it has some information of the problem. So the root is kind of not known, but at its trotterization you have trotter evolution, so it might be a little bit faster, and the inset shows the minimum energy that I get during the algorithm, right? So you can see the CD inspire is very close to the ground state, and this is the hardware efficient part, which is like slightly higher. So the conclusion is, for this problem it works better. So our algorithm works better, and it reaches to the ground state, near to the ground state, in not lower number of steps, but yeah, better approximate solution. But the question I have is, it's very hard because it also depends upon the classical optimizers that you choose. It also depends upon the initial points and many things. So like, if I want to make a statement that, oh, my algorithm is the best, then I have to be very careful because there might be some step size of some random classical optimizer which I don't know of, which might perform better. So yeah, but it looks good. So I mean, the first impressions are good. I compare 13 qubit system with QAOA, P equal to 1, so like only 2 parameters for QAOA, and in my case, the parameters are, each gate has its own parameter, so this is, you get a huge advantage with respect to QAOA, and this is, the circuit depth with this is higher than the circuit depth than this because you have 5 local interactions that you have to put in the Hamiltonian, in the circuit. So yeah, so this is pretty trivial, so it's fine. And the last one, I study 9 qubit system with the presence of noise. So I take a random IBM device, I take the noise from that, and then I just try to understand how the landscape changes with respect to noise. And it works pretty good, but not that great because the energy is shifted a little bit, right, because of the noise. But it's still, you can see that within like 20 iterations of the algorithm, you can get very near to the ground state. So it's kind of a good sign, right? But yeah, I have to further analyze with respect to concrete noise and which noise affects. But yeah, for this project, I've just taken the noise from the IBM and I've just put it in my sensors, and then I've studied if it converges or not, but it does converge. So yeah, that's also a good sign. Okay. So yeah, all the with respect to hardware efficient, QAOA and noisy also, it performs good. So the first signs are very good. Okay. I also did experimental implementation. I did experimental implementation with 3 hardwares. I have continuum trap diodes, I have IBM superconducting chips, and Google quantum virtual machine. So I didn't have access to Google real device, so I just deal with what I have. So I just did it with their virtual machine, which is very similar to the hardware, but it's an emulator, it's not the real device. And why I did it? Because I wanted to study how the algorithm performs under different connectivity and different native gates, right? So the connectivity for continuum trap diodes is all-to-all. IBM superconducting chip is linear, and then we have, for Google, it's a grid, so it's like a 3x3 grid, for example, right? And these are the native gates, which is fine. And the device is 20 qubit system, 16 qubit, and then 23. This is the hardware details. Okay, so first, continuum trap diodes. So I studied 2 systems. First is the 13 qubit system, and second one is the 17 qubit system. Okay, so here you have the connection of the qubits in continuum, and then these are the connections that I don't know if you can differentiate the color or not. You can differentiate the color? No, right? Yeah. So okay, just forget it. It's fine. So so I get a ground state. So okay, one important detail: to run this algorithm, I run the algorithm classically. Okay, and then I take the optimal circuit and I just put it on the device and then see the success. Okay, so this is a trick, no? No, it's not. It's not because right now I don't have any access to hardware which I can do the full algorithm of. Even in IBM, it's very difficult to do the full algorithm with noise. But I have seen in literally every paper that these guys do stuff like this. So I have seen paper of Google. They do just QAOA and they do the same thing. So yeah, so that's one. Someone will not like it, but that's how it is. So yeah, this is just one circuit that I've implemented, and this is the protein, full protein that I have, and this is the connection, as I mentioned earlier. And this is the largest protein that has been shown on an actual quantum computer, the 13 qubit system. The previous record was 9 qubits, and this one is 13. So we shift one amino acid, and then yeah, and you can see that it's like more than 80% success, which is mind-blowing to me, because 13 qubit system with more than 80% success on a real hardware is like amazing. So yeah, with that I do 17 qubit system also, but 17 qubit system I cannot find the ground state. So I landed up at the 4th excited state using my algorithm, right? So this success probability shows the probability of getting 4th excited state. Because I tried many times, maybe it's not expressive enough, my circuit answers, or maybe it's just too large a system, but I cannot find the ground state. So we just do the experimental implementation, and we found that, okay, The fourth excited state is like around 79% success probability, and this is the actual ground state protein, and my protein looks like this. Completely weird, but yeah. And then there is one overlap you can see here, but it's not clear, so I will not go into that.
This graphic is a little bit tricky because the second one is over. I thought that you got the higher probability. I want to ask you why, but it's over 0.8.
Yes, yeah. That's true. Yeah, I should change that anyway. Yeah, I actually did with 1 and then someone told me to change it because it looked not asymmetrical, but it's fine. Okay, so next is IBM and Google devices. What happened? Okay.
It's the same thing. The one in the right is double twice the one in the left.
Yeah. Okay, so yeah, this is the IBM, so this is the device, and this is the qubits that I choose, and this both are 9 qubit systems because we don't have all-to-all connectivity, so maybe higher qubits will not be possible, and this is the Google's QVM, which has 3x3, so 9 qubits and 9 qubits, and this is the connectivity, and these are the proteins, and I get around 22% success probability here, and I get more than 45% success probability here. But this is QVM, so maybe if you go to real device, there might be a reduction. But anyway, because of the swap gates, you get a higher probability in this one because you have to use very low number of swap gates. Yes, so that's more or less it. And to get all this solution, it's not that easy. You have to do, depending upon the hardware, you have to do many things, right? And yeah, you can see that because of the connectivity, I have to do lots of things in IBM. But Continuum, it's very easy. You have to, so in Continuum, depending upon the device, they have a limitation of 5 parallel operations at a single time slice, right? So I have to rearrange my circuit so that I don't exceed that parallel operations, and then I have to do the algorithm again and optimize again, and then yeah, and then native gate compilation, yeah. So you don't use CNOTs, you do everything in ZZ interactions, so that your native gate compilation doesn't increase the circuit depth. So and then no swap gates because you have full connectivity. In IBM, yeah, you have to do circuit rearrangements, as you said. You have to parallelize as much as you can, right? So you should be maximizing the interaction. And yeah, one more question is that how do you choose 9 out of the 16 qubits, right? So for that, but they have done a subgraph isomorphism algorithm where they find 9 out of the 16 and they do algorithm and they minimize the 2 qubit gate error. So it's another algorithm which finds the best 9 qubits, right? But it is not recommended, but it's just 9 qubit system, so I just did it. But when you go, this subgraph isomorphism are complex algorithms again. So if you want to go to 50 qubits, then you don't want to do this added complexity on top of already you have, right? But yeah, it's easy. So and swap strategies. So swap strategies is, as you don't have full connectivity, you have to apply swap gates, right? So best to get full connectivity out of a linear chain, you need 32 swap gates. That's the best I know of. I do it in 30 because there are some gates, some connections that are missing in the Hamiltonian. So that is just one lower number of swap strategies. But yeah, I can do the 9 qubit system in 30 swap gates. Okay, and then I have pulse optimization and native gate compilation. So in my circuit, there is no gate. I do the pulse level transpilation. So I replace every gate with a pulse, with a freely length pulse, and then it's easier because it compresses the circuit even more. So if you want to do C0, you have a full pulse, and then you can compress it via optimizing. And then these are normal things, dynamical decoupling to avoid the qubit idling, and then you have measurement error mitigation. And yeah, same thing with this. But here, as we have 2D grid, you need a lower number of subgates. So you can do it in 11. Yeah, so challenges, I already mentioned most of it. Sensitivity of initial parameters, you need to find good initial parameters, which is very challenging. Heuristic choice of CD operators, yeah, this one is interesting. So I have even if I do 2 order, I have a long number of gates. And then why did I choose these 2? Why not this, or why not this, or why not any of the combination, right? Yeah, this is the question that I am trying to find the answer of. But for this work, it's just heuristic. There have been proposals on how to select it based on machine learning and based on gradient of their answers and these kind of things. But yeah, in this work it's just heuristic. I find,
Shouldn't it be driven by the hardware?
yeah, that's true. Yeah, you can do that. Yeah.
Because if you have IBM and you have the processors, normal idea would be to take X1.
Exactly. Yeah, that's a good choice. Yeah, I mean, if you want to do, but maybe y plus yz performs better, then you have to make a choice. Like on a logical level, y plus yz performs better than y plus xy, then you have to make a choice, no? Then which one to choose. So yeah, but that's one of the options, that you just concentrate on what hardware you are using, and then just find gates depending upon your hardware, or you choose that which answers is performing better in my logical space, so which is giving me a better solution, then you choose and then you try to reproduce the result in the hardware. So this you can do.
There should be always a way, because it's always a close, let's say, there is always a unit that connects what you want to what you want, right?
Yeah.
To find really the optimal
Exactly.
to account the speed or
Exactly.
the amount of resources you have, or is quite hard.
Yeah, exactly. So that's it. And people have tried to do it based on gradients. So you find gradients of everything and then you select it. But yeah, okay. I will try to quickly. So biggest question for me is scalability. So if you ask me that if I have 50 qubits, will this algorithm work? My answer would be, give me 50 qubits and I will try. Right? I cannot say yes or no. So yeah, and there is no way I don't know personally there is a way to do this, how to show that if it's scalable or not. But yeah, and okay, I will skip. How much time do we have? It's done, no? More or less? Yeah, exactly. So I will skip the circuit evaluations part, it's fine. And yeah, that's the conclusions. We propose a new algorithm and the circuit depth is decreased because instead of implementing 5 local interactions, you just compress it to 2 local interactions, and we get good answers for optimization. And this answer has not been limited to protein folding. We did factorization, protein folding, portfolio optimization, and in every answers we get good solutions. So yeah, so that's it. Thank you so much for listening, and I will share the protein folding 20-page appendix so that you can read it and then maybe we can discuss. Yo, thank you so much.
So I think that we cannot complain about questions today.
No, it's fine. I mean, I'm happy to answer questions as much as I can. After that, I will try to give you 20-page, 30-page things and you have to read it and then we can discuss. So yeah.
Okay, thank you.
Yeah, thank you so much.